So we're going to look at our next problem here. And it's the same type of idea. It's just going to relate now to the concept of physical motion, which we've looked at before. So little recap of that, little refresher. If we have a function s of t, so the original function is the position of an object, then if we take the first derivative of that, that gives us the velocity. So that's changing position over time. So remember, we could have written that as like changing position ds over changing time dt. So yeah, that's going to be the velocity for the first derivative. And then the second derivative is, again, changing the first derivative over time. So changing velocity over time would be acceleration. So we go position, velocity, acceleration, and those are our function and its two derivatives. So in the past, we've done like, okay, you're given the position function, and then we take derivatives to get velocity and then acceleration. But now that we have the antiderivative, we can work backwards. So if we are given the velocity or the acceleration, we can work backwards and use the antiderivative to find the position function, s of t. Okay, so that's what we're going to do in this next problem here. It tells us that a stone is thrown vertically upwards from the edge of a cliff that's 100 meters above a river. The initial velocity of the stone is 40 meters per second. And then we're going to find the function that models the stone's position above the river. And there's a little note here. Acceleration due to Earth's gravity is about 9.8 meters per second squared. So that's a useful constant, especially in physics, comes up a lot. If you're working in English or American units, you could also write this as about 32 feet per second squared. So that works. But make sure to use whatever units your problem is using. So since ours is in meters, 100 meters above a river, 40 meters per second, we're going to want to use this 9.8 meters per second squared for acceleration in this problem. Okay, so let's draw a little picture of what's going on here. All right, so we have a cliff. Okay, and it is a very steep drop here. Okay, that's the cliff. And at the bottom of the cliff, there is a river, like so. Okay, color it all in. Yeah, okay. So there's your cliff and your river. So we are told that a stone is being thrown vertically upwards from the edge of this cliff, and it is 100 meters above the river. So 100 meters from the top of the cliff to the surface of the river. And here's our little guy or gal or whatever, something is throwing a stone upwards from the edge of the cliff here. Okay. So that stone is going to go up, and then we know what goes up must come down. So the path of the stone would go something like this. It's going to go up until it reaches a certain point, and then gravity is going to pull it back down, and it's going to fall into the river eventually. Okay. So there we go. That's a picture of what we're looking at. And notice how we do have a numerical measurement here, 100 meters above the river. Now, when you're drawing your own picture and kind of setting up your own problem doing things like this, you can choose which way you want your coordinate system to go. for instance, you could say that you're going to set up your coordinate system so that the surface at the top of the cliff is your 0 point. And then the river that would be down at like negative 100 meters. But personally, I prefer, I think, to set the surface of the river as 0. So this is like a 0 position, S equals 0. And so we'd be starting up at positive 100. So positive direction this way and negative direction this way. That just makes a little more sense to me. Okay, so I would say here we are starting up at 100 meters. So that's our position at time 0. So time t equals 0 is right here. S of 0 equals 100. Okay, let's write that down. Oops, not S of 100. S of 0 equals 100. 100 meters. All right. Now for our other values here, we have the initial velocity of the stone, 40 meters per second. So that is the initial velocity when it's being launched upward as it's leaving the hand or the cannon or whatever's on top of the cliff here. That is our starting velocity, 40 meters per second. Okay, that velocity is going to change as the stone goes through its path, but right at that instant, we got 40 meters per second. Okay, so we have some conditions here, and now we're going to need something else. We're going to need an actual like T equation to start working with. So there is this other detail that we haven't used yet. Acceleration due to Earth's gravity is about 9.8 meters per second squared. That's actually where we're going to get our starting equation from. So this is a constant acceleration. And that is going to be our acceleration function, because the acceleration at any point in time throughout this rock's little journey is going to be 9.8 meters per second squared. But we've got to think for a second about the direction in which gravity is acting. So gravity is pulling things back down towards the earth, we would say. And so gravity is acting, according to our picture, in the negative direction. Okay, it's pulling the rock back down. So when we write our acceleration function, we're going to be writing negative 9.8 meters per second squared. The units on here are optional. The function itself is a of t equals negative 9.8. And I'll make a little note here that gravity is acting in the negative direction. Okay, that's why we use negative 9.8 instead of positive. Notice that the velocity was positive because the stone is being thrown upwards in that positive direction. So initial velocity is positive, initial position is positive, but acceleration is going towards the negative. Okay, so that's what we can get from the wording of this problem. Now, to put this more in terms of what we were just looking at, differential equation style, we're going to use our facts about physical motion from right here up above. The acceleration function is the second derivative of position. So what we've actually been given here is that s double prime of t equals negative 9.8. Okay, so instead of writing like a of t, you could write s double prime, and now it'll look more like a differential equation. Okay, and then we're also given these two conditions. So with s of 0 equals 100, and well, v of 0, velocity is our first derivative of position, so that says s prime of 0 equals 40. Okay, so this together makes up our differential equation, or diff EQ for short. Okay, so we're going to solve this in the way that we were just doing for that second differential equation problem. We could use this secondary approach here, or we could find our constants as we go through. Okay. Looks like Felipe's got our first antiderivative ready for us. So cool. We're going to take that s double prime of t and go back to find our first derivative. So use the antiderivative here to get s prime of t. And yeah, negative 9.8 t plus c. Hey, good use of the t there as well, Felipe. Keeping it in the variable that we want to use here, using t instead of x. I appreciate that. And then, yeah, we're going to use v of 0 equals 40 to find that constant. So find c. So this is working it through the first way that we did that other problem. So s prime of 0, or v of 0, you could say, equals 40. And, well, s prime of 0 would just be negative 9.8 times 0 plus c. So it would just be c equals 40. Okay. So we're plugging in 0 to the s prime. Negative 9.8 times 0 plus c would just be c. And so we get c equals 40. Yeah. All right. And so that is the first derivative. That's our velocity function. Negative 9.8 t plus 40. And so to get back to position, I'm going to need a little extra room here. So let me zoom out and make a gap in the pages. Just a little bit. Okay. Zoom back in. Because, yeah, we've got our first derivative now, and we're going to want to use that antiderivative again. So do an antiderivative there, and that'll take us back to our original function level. And so, yep, our steep's got it. Very good. Negative 9.8 divided by 2, t squared, plus 40t plus c. Very good. And we're going to find that constant c again, using this time our other condition, s of 0 equals 100. Okay, and so you would plug in 0 for that, so negative 9.8 over 2, 0 squared plus 40 times 0. That part's not very exciting. Okay, so here's s of 0 on one side, a lot of the terms 0 out there, and we end up getting c equals 100. Okay, and so that will give us our answer here. The answer for the position function, it's going to look like s of t equals, let me actually just simplify that first. Yeah, Felipe, you simplified it too. So 9.8 divided by 2 is 4.9, so we can just do that. Negative 4.9 t squared plus 40t plus 100. And there we go. So that is our position function. So you could find the position of that rock at any point in time by plugging in whatever t value you were interested in into this equation here. So yeah. Oh, you forgot the negative on 4.9, but yeah, now we got it. Cool. Okay, so that's a differential equation applying to physical motion. The hardest part on that really is getting the setup, I guess, finding that initial position, velocity, acceleration, kind of being able to pick out those things from the problem. But once you see kind of how one of them goes, that's usually how the pattern will look there. Okay. So yeah, once you know what to look for, it turns out okay. And then it just basically runs like that previous problem we had done. Find the different constants, do your antiderivatives. Okay. So yeah, those are differential equations.